This video contains the solutions to take-home problems number 26. For this first problem, we're told that we have a colony of mosquitoes that has an initial population of 1,000 and a growth constant k equals 0.02, where t is measured in days. So our standard form for our exponential growth model is that a equals a naught, or a0, times e to the kt. So a naught, that's the initial amount, and then k is the growth or decay constant. If k is positive, it's a growth constant, and this represents exponential growth. And if k is negative, then it represents decay, and it's exponential decay. So we're told that the initial population is 1,000. We're told the growth constant is 0.02, so that allows us to figure out that our formula is 1,000 e to the 0.02 t. So now what are they asking us for? They want the population after 5 days, so in other words, we want to know what's the population when t equals 5. So when t equals 5, we have a equals 1,000 times e to the 0.02 times 5. And when we put that on our calculators, we get 1105.17. Now we can't have a fraction of a mosquito, so we're going to round that to the nearest whole number, and that's 1105 mosquitoes. Continuing with the same problem, now we want to know how many days it will be until the population reaches 2,000. Remember that our model for this problem is a equals 1,000 e to the 0.02 t, and so now we're told that the population we want to be 2,000, so we put that in for a. So this gives us an equation that we can solve. We need to get t by itself, and since t is trapped in an exponent, we need to get the exponential term by itself, and then we'll use logarithms to get the variable out of the exponent. So we're going to start by dividing both sides by 1,000. Again, we want to get the exponential term by itself. We can't start using logs yet until the exponential term is by itself. 2,000 divided by 1,000 is 2, so we get 2 times e to the 0.02t. And now we can rewrite this in log form. This is an exponential equation. Our base is e, so we have the log base e of the result, which is 2, equals the exponent, which is 0.02t. Now remember that log base e is better written as ln, and so this is really just ln of 2 equals 0.02t. I didn't do any operations there, I just realized that log base e is represented by the notation ln. And then if we want t, we just divide both sides by 0.02, so we get ln of 2 divided by 0.02. Putting that on our calculators gives us 34.657. We're told to round to the nearest whole number, so that's going to be approximately 35. In this case, that was t, so this is 35 days. So we have a new problem here. So now we're told that we have an initial population of 500, and then we have 800 bacteria after 1 hour. So here we're going to actually have to figure out the growth constant using this information. So our basic model is a equals a0 times e to the kt. We at least know that a0 is 500. We don't know what k is yet, but we know that a0 is 500. So we have 500 e to the kt. So we have to use the fact that we know that we have 800 bacteria after 1 hour. So what they've told us is that when t equals 1 hour, the amount is 800. So putting that information into our equation gives us an equation that we can solve for k. So that looks like 800 equals 500 times e to the k. Divide both sides by 500. That's going to be 1.6 on the left and e to the k on the right. Rewriting that equation in log form gives us ln of 1.6 equals k. We want to round this to 2 decimal places, so we put this on our calculator, and we get that k is approximately equal to 0.470003, and that's going to be rounded to 0.047. Now that we have our growth constant, now we can answer questions like this. How long will it be until the population reaches 5,000? So we have a equals a0, which is 500, times e to the k, and we just figured out that k is 0.47, times t. So we want the population to be 5,000, so we put 5,000 in for a, and now we need to solve for t. Divide both sides by 500 to get the exponential term by itself. That gives us 10 equals e to the 0.47t. Rewriting that in log form, we get the natural log of 10 equals 0.47t. Solving for t, we get natural log of 10 divided by 0.47. Now we can put that in our calculators, and we're going to get 4.899, and that's hours. But if we read the question carefully, we're asked to round to the nearest minute. So what we need to do is we need to figure out how many minutes are in 0.899 hours. We know that this is going to be 4 hours and some number of minutes, but the question is how many minutes? And so what we need to do is multiply 0.899 by 60, because 0.899 is a number of hours, and there are 60 minutes per hour. In this case, the units hours will cancel out, and we get 53.94 minutes. That rounds to 54 minutes, and so that means that the population will reach 5,000 in 4 hours and 54 minutes. Here we have a radioactive decay question. We're told that the half-life of this element erbium is 10.36 hours, and we have an initial sample of 500 grams that's been being monitored for 24 hours. And we want to know how much of the sample will remain at the end of this time. So we don't know much about this situation. We know that we have our standard exponential model, a equals a0 e to the kt. The half-life is going to be used to figure out k, and we also know that our initial sample is 500 grams. So we know that a0 is 500, and now we need to figure out what k is. So when they tell us that the half-life is 10.36 hours, that means that when t equals 10.36, the amount will be half of what we started with, which is just going to be 250. So putting that information into our equation, we get 250 equals 500 e to the kt, where t is 10.36. Divide both sides by 500 gives us 0.5 on the left, and e to the 10.36k on the right. Rewriting in log form, we get log of 0.5 equals 10.36k. Dividing both sides by 10.36, we get the natural log of 0.5 divided by 10.36, and we can put that in our calculators. That's going to give us negative 0.066906. We want to include a lot of decimal places here because we're not done with the problem. At the end of the problem, we're going to have a number of grams, and we're told to round that to the nearest whole number. But if we round too soon, then that's going to throw off the answers that we get later. So especially with growth and decay constants, you want to include a lot of decimal places just so that your answer is as accurate as you can make it. So in this case, I'm using 6 decimal places because that's going to help me keep my answer being very accurate. Okay, so now we want to know how many grams are left after 24 hours. So we want to know what's the situation when t equals 24. Well, we're going to have the amount, which is what we want, equals 500 times e to our growth constant, k, which is negative 0.066906, multiplied by our time t, which is 24. Putting that in our calculator, we get 100.37, and then rounding that to the nearest whole number, we get 100 grams. Similar situation here, we have a radioactively decaying element. We're starting with a sample of 10 milligrams, so we know that's going to be our initial amount. And we're told that after 20 minutes, the sample has decayed so that it's only 8 milligrams. And we're asked to find what the half-life is. But let's do one step at a time. The first thing we're going to need to figure out is our decay constant. So we start with our standard model, a equals a naught e to the kt. We know that the initial amount is 10, so this is a equals 10 times e to the kt. And now we need to use the information that after 20 minutes, we have 8 milligrams. So what that tells us is that when t equals 20, the amount equals 8. Putting that in our equation, we get 8 equals 10 times e to the k times 20. Divide both sides by 10, we get 0.8 equals e to the 20k. Rewriting in log form, we get natural log of 0.8 equals 20k. And finally, dividing both sides by 20 gives us natural log of 0.8 divided by 20. Throwing that in our calculator gives us negative 0.11157. Again, I'm using 6 decimal places to try to keep my answer to be as accurate as possible. So now we need to know the half-life. So we want to know how long does it take our sample to decay to be half of what it started with. So in other words, when will the amount be half of our initial amount, half of 10, which is 5? That's the question. So plugging into our equation, we get 5 equals 10 times e to the kt. We know k now is negative 0.011157, and t is what we're looking for. We want to know at what time will this happen. So we divide both sides by 10. That gives us 0.5 equals e to the negative 0.11157t. Rewrite that equation in log form. Gives us natural log of 0.5 equals negative 0.011157t. Divide both sides by that value of k, so we get natural log of 0.5, all divided by negative 0.011157. And when we put that in our calculator, we get 62.127. We're asked to round to the nearest minute. T was measured in minutes, right? We had 20 minutes, so everything has already been in minutes. So this is 62 minutes. And that's our answer.